This is Thaxted, a small village in southeast England. 500 years ago, it was an important cutlery manufacturing town. The cutler's lane, the recorder's house, and the cutler's hall still exist. But of the industry itself, Thaxted is called today the Sheffield of medieval England. But the only steel worker left there is the village blacksmith. While iron and steel were made from ironstone and charcoal, Thaxted remained famous for its cutlery. About 400 years ago, the workers in the Sheffield valleys developed the use of water mills and began to use coal in place of charcoal. And so the industry of Thaxted and the craftsmen gradually moved to the north, many of them to Sheffield. In the Firth Brown works, the traditional and hereditary skill of the craftsman has been developed over more than a century. Today, these works, covering an area of 80 acres, employing over 8,000 people, are specially equipped to produce high-grade steels of all types and in many forms. These electric arc furnaces have a melting capacity of 10 to 30 tons each. Immediately after tapping, the furnace is recharged with selected high-grade steel scrap and other steel-making elements. The roof then swings back, and melting proceeds under the action of 16-inch diameter graphite electrodes with an electrical input of 5,500 kilovolt amperes. It takes about 2.5 hours to reduce this 30-ton charge to a molten state and to reach a temperature of approximately 1600 degrees centigrade. The slag, which is a non-metal layer above the molten steel, is formed by additions of ore, lime, fluorspar, or silica sand. This reduces the amount of the undesirable element, phosphorus. After the oxidizing period is complete, the slag, which has absorbed the unwanted phosphorus, is removed. Now, and during the whole refining period, frequent samples are taken for laboratory analysis in order to check the composition of the bath. A more rapid check of the general condition of the molten steel is obtained by expert examination of the crystalline structure of a fractured sample. The second slag for the reducing period is made by additions of lime and ground carbon for the removal of sulfur and oxygen. A stopwatch in the hand of an expert is a ready means of estimating temperature. In this mirror test, the sample passer observes the time taken for a liquid sample of the steel to form a solid skin. At this stage, the additional alloying elements required can be calculated. These are carefully weighed and added in order to produce the desired composition. The bath is then stirred or rabbled to ensure thorough mixing for uniformity of steel and temperature. To make sure that the steel is at the correct temperature for casting, A final reading is taken by means of the immersion pyrometer. Temperature and composition are right. Work on the furnace stage is complete. The preheated ladle is brought into position. The current is cut off. Up go the electrodes, and as the furnace tilts, 30 tons of finished steel pour into the waiting ladle. Temperature observations are taken with the optical pyrometer throughout the tapping and casting operations. Meanwhile, the ingot molds have been dressed and preheated, ready to receive the molten steel. The casting or teaming of the ingot must be carefully controlled, both as regards the flow of steel and its temperature. Each particular size of ingot requires a definite speed of teaming, and the design of both mold and feeder head play an important part in ensuring freedom from unsoundness. After annealing to reduce internal stresses, the ingots are turned to remove surface blemishes. The ingots are then reheated and reduced to billets by rolling. The rolls and rolling procedure are designed to give gradual reduction of the ingot to the size and shape of billet required. We have shown you examples of just two of our many products. The same care in manufacture and testing which has gone into them is applied to all Firth Brown products. This modern age calls more and more for high-quality alloy steels. Steels of greater strength and less weight, steels to withstand greater stresses and higher temperatures, to meet the ever-increasing demand of engineers throughout the world for improved performance and speed. The electric power which feeds factories and farms as well as homes and cinemas depends on high-quality steel. The plant and generators rely on sound steel. Without it, the modern power station would not be possible. The overhead cable would no longer carry its potential energy into every corner of the country. The railway systems of the world depend on steel, high-quality steel, for their speed and safety. Many tires and wheels, pistons and cranks and countless other component parts are made from alloy steel. I am happy to name this ship Rangitani. I wish success to her and to all who sail in her. These stirring words have started ships down the slipways for centuries. From days of sail to those of reciprocating engines, to the steam turbine, and now in the future the marine gas turbine, ships have been launched to swell the world's mercantile marine. Famous ships, oil tankers, colliers and small fishing boats are all dependent upon special steels to produce the motive power to enable them to carry out their work with speed, confidence and safety throughout the oceans of the world. Cement production calls for large quantities of special manganese and other alloy castings for use in its huge rotary kilns and other plant. The temperature inside these kilns, about 1100 degrees centigrade, indicates the onerous conditions under which steel serves this industry. Quarrying and mining equipment is subject to severe abrasion and very heavy work. Here, by way of an example, are digger teeth produced as manganese alloy steel castings in the buckets of these massive excavators. Gears and other components, subject to heavy stresses and wear, are also manufactured from alloy steel forgings and castings. In contrast, the textile industry, with its spinning frames and looms, like other complicated pieces of machinery used in 1001 industries serving our daily needs, must employ special steels. Probably the most spectacular application of our special grades of alloy steels is in the aircraft industry. Not only steel for the engines and aircraft themselves, but also for the machine tools and cutting tools used in their production. Rapid development of the jet and turboprop engine has only been made possible by the closest collaboration between designers and steelmakers to provide the special steels capable of withstanding the high stresses and strains met with in aircraft flying at speeds near that of sound, the giant airliners and flying boats weighing as much as 130 tons. New aircraft all have their special problems. Increased weight, higher landing and takeoff speeds bring an increasing call on alloy steels able to perform satisfactorily under increasingly severe conditions of service. Even these old Crocs used alloy steels, and if the aircraft industry needed alloy steels 40 years ago, how much more does it depend on its high quality and uniformity today? Let these modern aircraft speak for themselves, but there is surely no finer example of the quality of these steels under the most exacting conditions of service. We have tried to show in these few examples the important part played by the steelmakers in the lives of us all. The skill of the steelmakers from melting to casting, from rolling to forging, the constant works checks and laboratory tests justify our faith in the excellence of the resulting products. Firth Brown, with its research facilities and wealth of experience on all metallurgical problems, is always at the service of the designers and engineers throughout the world, who can be assured of obtaining the best steels for their requirements, confident in the knowledge that it is indeed sound steel.